All right, so here we are with 9.5, which is our last chapter of last section of chapter 5, and we're talking about infinite geometric series. We're actually not going to be talking about mathematical induction, but we will be talking about the infinite geometric series. So we are going to find sums of infinite geometric series, and we will not be doing this mathematical induction, but feel free to take discrete mathematics and you can do all you want with that. All right, so here we are with the definition of an infinite geometric series. Basically, remember, series is that you're going to add a bunch of numbers, and geometric means that you're going to add a bunch of numbers that continue to grow exponentially. So it may be interesting to try to actually get a series to become a number other than infinity in your mind. So in this case, the sum of an infinite geometric series is given by this formula here. So it is on your formula sheet. Some people tend to draw a little infinity symbol here because remember that the little tiny number here is how many or the n number of terms. And of course, we are trying to find an infinite number of terms, so we could potentially put infinity there, but it is standard if it's not there. So as long as the ratio r is less than 1, and we'll kind of talk about what that means in a little minute here, but the idea is that you're going to get this sum of the infinite series if you take the first term and divide that by 1 minus that constant ratio, or that common ratio. So remember that's from taking the next term divided by the previous term, and then you have that number that you would multiply. So here's our formula. However, for this formula to work, especially when you're thinking of this key piece here, what needs to happen is something called converging. So if something is converging, it means that it's getting, well, in this case, noticing your value here, it's getting more and more constant. And so in that case, more and more predictable about what the number is going to become. So as you can see here, if this is 0.4, this is going to be 0.10. And so you can see that what's happening is it's converging on 0.10. And so 1/10 is where it's converging. And so you can guess that infinitely many times it's going to kind of approach that number. So in order to converge, a geometric series has to have an r, that common ratio, that is less than 1. And so it can be a negative, what we would call a fraction, or it can be a positive fraction, again, something less than 1. And if that happens, so if it's that decimal or fraction, that partial sum or that infinite sum approaches a fixed number or a limit. And so because it approaches that fixed number, and especially that fixed number as becoming 0, what's going to happen is you can then predict what's going to happen infinite amount of times after that. So that's the idea of converge. And so the opposite of converge is diverge. And so that means that rather than noticing your asymptote here as a vertical line, more or less, the previous one was a horizontal line. And so we are no longer coming to like one number here, we're actually expanding until infinity. So this is a diverging. Your r is going to be greater than or equal to 1, because if it's 1, then it's going to increase each time. But if it's less than 1, again, that's converging, but greater than or equal to 1 is going to mean that it will diverge. And so it does not approach a fixed number as you add and add and add. All right. So again, the idea is converging. We're going to have smaller and smaller values. Added until it's like adding 0. Because there are only so many decimal points that you can kind of round to in a certain number before you really are just adding 0 each time. This next one here is diverging. And again, this is because you are getting larger and larger values. So larger numbers continually added. So you're adding and adding. Even if it was just 1, you're continuing to grow bigger and bigger each time. And so that's why 1 is included, as well as anything larger than that. All right, so we're going to go ahead and determine whether it is convergent or divergent. So we are looking for that common ratio. And so remember that if it's going to converge, we're talking about an R that is less than 1, or an absolute value of that R. So even if it's negative, as long as it's that negative fraction or decimal less than 1, you're fine. And then if it diverges, that's where your R is going to be larger than or equal to 1. And of course, that could be the negative value of it as well. So got your absolute value signs there, which I normally make or try to make thick, but anyway. All right. So we're going to find our R value, and remember that to get your R value, you can kind of just look at the pattern, or you can take a next number and divide it by a previous. So I'm going to take this next term, divide it by the previous term, and I now know that my R is 0.1, which of course you can see if you take 1 and multiply it by anything, you're going to get 0.1. All right, so then we just have to double check, is that greater than or equal to 1? So in that case, notice that 0.1 is less than 1, and so that means, because it's matching this piece here, that this series will converge. All right, so our R value of 0.1 is less than 1, and so therefore we come up with it converging. All right, then the next one, again, we're trying to take our next term and divide it by our previous term. So 12 divided by 4 ends up getting us an R of 3. And an R of 3 is definitely larger than or equal to 1. And so because of that, we're going to say that this series diverges. And so it will not become one number in the end. It will become infinity that keeps growing. All right, so then we're actually going to find the sum of the infinite geometric series. And so since it's not written on here, we'll take the time to write that formula. Again, the idea is that the series of infinite number of terms is going to equal the first term over 1 minus that common ratio. Since they're asking you for the infinite geometric series, and it says if it exists, we do have to do the idea that we did in the previous examples, double checking that that number will allow it to converge so that we can find the infinite geometric series. So the first thing we'll start out doing then is finding R, and so that's going to take this negative 0.2 and divide it by a positive 1. And so clearly anything divided by 1 is going to be that same number. So this number here, its absolute value is going to be less than 1. And so because, again, it is less than 1, we're going to talk about this converging. So this idea here just told us that we can continue. But of course, if it said that it diverged, we would not be able to get this term. So you can, of course, plug in whatever numbers you want into here, but it will not actually be true unless it's a converging series. So in that case, we are then going to take our first term, which is 1. So we've determined that our first value, or a sub 1, is 1. An R we just found out was negative 0.2. And so we're going to plug each of these pieces into this formula. So the infinite series is going to be 1 over 1 minus negative 0.2. And so if we continue to add and add and add each of these numbers, and in fact subtract a few of them, it's going to be like we are adding 0 and subtracting 0 towards the end. And so we will come up with 1 over 1.2. And so this series, infinitely added, is going to become 1 over 1.2. So 0.833. or 5/6. Just to mention that that's 0.83 repeating. Okay. So again, all we did was 1 over 1.2. And then, of course, to convert something into fractions, in your math button here on your calculator, you can pick the arrow with the fraction bar or fraction word, and then it will change. If you have a repeating decimal that can be a fraction, it will change it into a fraction. All right, so find the sum. Here it is. This is the sum, and it existed because our value was less than 1. All right, so then our next piece here, again, we're trying to find out if it converges or not, and so we need our R value. These are the type where we can actually just identify what the R is by the fact that it's sitting right here. It's that multiplier that's being raised to a power. So R is 1/2. And 1/2 is less than 1. And so because this R value is less than 1, we can continue because it converges. Again, I've mentioned, but you can in fact use this infinite sum equation, and you will be able to actually get a digit if it's divergent, but that's not necessarily the true value. So just plugging things in doesn't necessarily make them true. All right, so here we are with our first term, and our first term comes from taking 1/2 and raising it to the number 1, because that's going to be our first term, minus 1. And so that means that we're going to take 1/2 and raise it to the 0. And so, of course, anything raised to the 0 is 1. So we've just found out that our first term is 1, and that our R, we already knew, was 1/2 from the previous work. So now we can go ahead and plug in our A and our R in order to find our infinite sum. So our A1 was 1, and we're going to do 1 minus 1/2 because that's the R value. And so that means it's 1 over 1/2. And how many halves go into 1? 2. So the sum of this pattern here, 1/2 to the k minus 1, is going to end up with 2. It's going to converge at 2. Just a side note about this notation here. Notice that this used to be our number of terms up here, but of course now we're at infinite. So they could ask you something like find the infinite geometric series, or without words, they can say find the infinite geometric series because of this infinity here. All right, so that's your 9-5 notes, and so you're just going to take each of those pieces of converging and diverging, and then also sums of geometric series, and do some examples in your assignment.